OrCAD Capture 9.2. That is the software we need for lab number 1, 2, and 3, right? So at first, I'm going to show you how to install this software. First of all, my DSH and MicroIn, these two software you do not need to install. These are portable. That means you can actually copy the folder and use it, okay? But OrCAD Capture Lite, this is the light version, not the paid version. So you have to install these each time you use it within a month. That means after 1 month, you will see the light version is gone. So you have to install it again. So in 1 month, it is not a problem. So I'm going to extract this, extract to my desktop. After extracting, I'm going to close it. I'm going to go to my desktop here, this one, OrCAD Capture Lite 9.2. Double click. Here you will see a system folder or setup. Here is a setup file. Right click, run as admin. Yes. Okay, next. Remember to click all of these, 1, 2, 3, because this one is not possible. So click all of these, then next, 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 next. Okay. It will be installed. Okay. Okay. So our software is okay, already done. Now we have to go to the VLSI Lab. This one. Here you can see at our first lab, we can see, in our first lab, we can see the name of the experiment is Introduction to Circuit Simulation using SPICE, Cmos Inverter. So we will be doing and simulation for Cmos Inverter. What is Cmos? Cmos is complementary metal oxide semiconductor, right? Cmos. What is complementary? Complementary means it always have two opposite side of things. That's why it is called complementary. That means NMOS and PMOS, if they are mixed together, combined together, that become a CMOS. Okay, so we will learn that later, no problem. Inverter. What is inverter? Inverter is a thing that inverts the logic. It is actually a NOT gate, nothing else. NOT gate, NOT, not. A NOT gate. What is that? NOT gate. What it does? It actually invert the logic. 1 becomes 0, 0 becomes 1. So let's go to the page. Introduction to circuit simulation using SPICE. SPICE is a software that is the PSPICE we already installed. We can actually simulate different types of things like diodes, BJT, JFET, MOSFET, common semiconductor device. We can actually simulate these. The CMOS inverter. This is a CMOS inverter or a NOT gate. This is a logic level, or logic level means gate level circuit. A NOT gate is there. If you give V in as input, you'll get V output. Always remember V out is equal to V in bar. That means it will be opposite. So if you give 0, you will get 1. If you give 1, you will get 0. So this is the switch level or transistor level circuit for an inverter. That means inside the inverter, you have these. Here you have two MOSFET. One is P MOSFET, another one is N MOSFET. They are connected together. Their drain is connected together. This is the source. This is the drain. This is the drain. This is the source. This is gate. This is gate. Okay. So source, drain, gate, source, drain, gate. Okay. This one. So here the drain are connected like this. and their gate are connected like that. One source, that means the PMOS source will take the VDD, that means the voltage, and NMOS source will take the ground. Okay, their gate, combined gate is the input, their combined drain is the output. That's it. So this is actually a what? This is actually a very big NOT gate. You have one output, you have one input, you have one power, you have one ground. That's it. Understood? So this is the switch level. Switch level means transistor level, simplified transistor level. There is one complicated transistor, or not complicated, that means detailed transistor level circuit as well. Okay, that is called circuit level. So this is a switch level diagram. Next one is the circuit level diagram. Circuit levels means transistor level, not simplified. Here, the only difference is you have a body. That body is connected to what? The body is connected to source. Okay? Body is always connected to source. That's why. That if you indicate that, that becomes circuit level diagram. Now, you have to write a code for this circuit. You have to write a code for this circuit. You cannot draw in the PSpice. In the PSpice, you cannot draw. You have to write a code. How you can write a code, I will teach you that right now. Okay? But before that, let's see the given, given code that is already given in the lab. Let's see that first. Here, these are the all description of writing the code. How you can write the code, the description is given. But we do not need that. We will explain that while writing the code. Okay, this is the simple Cmos inverters code that is already given for you. I'm going to copy it. Control C. I'm going to go to the desktop. And make a text document. Let's say Cmos not. Let's say Cmos not, okay? No space. Control V. So I copied some of the things, some of the part. Now rest of the part. Okay. That's it, right? So this is the code. This is the code that we have copied just right now. Now I will explain what is this. Let's get back. Okay. Circuit level, this one. Make it smaller. Okay, now everyone see, writing the code has few components. Remember, when you will be starting when you will start one line using star, that means there is actually a comment. Okay, this is a comment. These are actually comment. Comment means these are not effective in the code. Okay, so these are not necessary as well. Now, when you start the code using dot, dot means what? Dot means operation. Dot means what? Operation. So see this one. When you give dot tran, dot end, dot probe, these are actually operation. When you give a dot, that means this will take it as an operation. Now, when you start your line with plus, that is the specification. When you write the specification, you'll give plus. Here you are giving plus. And when you give nothing, that line is your what? That line is your specification, not a specification, sorry, circuit description. Circuit description, that is the circuit description you are going to give. So here, we are going to describe the circuit in our code. This part, the specification, this is the N model specification. This is the P model, that means the PMOS specification. Here you can see TOX. What is TOX? We'll explain later. KP, N sub, LD, mu O. A lot of things are there, right? Vmax, VT. What is VT? VT. Here is VT. VT is there. So a lot of specifications are there. These are actually depending on the material you are going to use. The material you are going to use, these things depends on that. These things depends on that. That means when you buy some silicon from the market, when you come back, your material engineer will inspect. Your material engineer will check whether the silicon is good or not, or what are the properties of the silicon. Okay, properties, all the properties. They will measure those properties and give you this data. They will measure the properties and give you the data. Now you have to use the data to what is that? To simulate the performance. Okay, to simulate the performance. Now you are going to use this data from your material engineer's report. Obviously, you are not going to do that because you are not the chemical or material engineers. No, you are not. You are an electrical engineer, so you will calculate or you will analyze the electronic part actually, all the electronic and electrical part. So here, so let's describe this. What is that? Describe this circuit in our description. Here, how many transistors do you have? 2, right? One is this, another one is that. So one transistor is MPD, another transistor is MPU. This is the naming. You have to name everything that is here. So remember, the transistor will start with M. Whatever the name you are going to give, M1, M2, M3, MA, MP, MC, let's say M Ashik, M Hafiz, doesn't matter. But it should start with M. M means MOSFET. Okay? Voltage will start with V. Capacitor will start with C. Resistor will start with L. Understood?
Yes.
Okay. So transistor, we have 2 transistors here. One is MPU, that means the transistor. You can call it MN, N MOSFET. You can call it like that, no problem. This one is MP. We can call it MP, no problem. Okay? Or we can call it like this, M1 and M2. Okay, we can call it, no problem. But I like MP and MN. Okay, we can write that. Why they have written MPD? They have given M pull down, M pull up. Pull up means, I will explain later, no problem. Pull up means it will pull up your output. That's why it is called pull up transistor. MPD, pull down, that means it will pull down your output. That's why it is called a pull down transistor. Pull down transistor means N MOSFET. Pull up means P MOSFET. That's it. Okay. Then this is your input. That's why it is V in. This is your output. That's why it is called V out. This is your CL. That means the load capacitor. That's why it is CL. This one is VDD because it is the power. And then after that, after doing that, you write the pin name: gate, drain, source, gate, drain, source. Okay? Gate, drain, source. Like that. Gate, drain, source. Always remember, NMOS has their drain at the top. PMOS has their drain at the bottom. Okay? Always remember.
Yes.
Okay. After doing that, you have a very important job to do, that is the noding. Not coding. Coding is later. Noding. You have to use noding. What is noding? Noding means, you remember the nodal analysis, right? From the circuit 1 or circuit 2 maybe.
Yes.
Nodal analysis. Yes, there you give some node in your circuit, right? Remember? You give some node.
Yeah.
Your ground is always 0. So this is your ground. So this is 0, right?
Yeah.
Okay. Next, after the 0, you have to give all the input. We have to go for all the input. Here, how many input do you have? Only one input, right? V in.
Yes.
Only one input V in. That's why that is your number 1. Remember, V in is actually a what? A pulse, right? V in is actually a pulse, right? So 1, that means the positive pin is connected to pin number 1. What about the negative pin? Negative pin of that V in. What is that? Obviously, that is grounded, right?
Yes.
That we already know. That's why no need to show it. No need to show it. Okay. Next, that is your V in. Do you have any more input here? No, no other input. Now go to the power, VDD. VDD is 2. VDD means a DC voltage, DC. So the positive is connected to 2. What about the negative?
Oh.
Is ground, right?
Yes.
Grounded.
So we know it, don't have to show it. Now then what node we are left with? Yeah, we are left with this node, right? Here we have a node.
3.
This is node number 3. Understood?
Yes.
Okay. Any more node? Any more? No, this is 0. This is connected to 0. This is 2. This is connected to 2. This is 3. This is 3. This is 3. This is 1, right? The gate is 1. Connected to 1, right?
Yes.
Okay. Understood? So
Yes, sir.
I'm going to highlight all of these again by using the bigger one. So this is 1. This is the node number 1, right? Okay. Let's use a different color. This is node number 2.
Source.
Source and the VDD, right?
Yes.
Node number 2. Okay. Next, use a different color. This is 3. Right?
Yes.
Next, use a different color. This is the ground. And the body is also
Grounded.
grounded. This is also ground, right?
Yes.
And here you have another ground, right?
The ground. Also the
Okay. Also the V in.
yeah.
So V in is in between 1 and 0. VDD is in between 2 and 0, right?
0. Yes.
Okay. Capacitor is in between 3 and 0. Capacitor is in between 3 and 0, right?
Yes.
You got it, right? Okay. Since you got it, we're going to write the code now, okay? How? See. This is MPU. MPU is the pull-up transistor. MPU. How it is connected? Give a space. 3, 1, 2, 2. That means this one, right? Where it is connected? The sequence will be drain, gate, source, body. Where the drain is connected? The drain is connected. Where it is connected? Which node it is?
3.
3, right? That's why
Yes.
3. Where is the gate? The green color, right?
1. Yeah.
1. Where is the source?
2.
Pink color, 2. Where is the
2.
body?
The board also 2.
Also 2, right? That's why it is 3, 1,
2. 2.
2, 2. Understand?
Yes, sir.
Okay. Space PENH, because it is a P MOSFET, right?
Yeah.
This is a P MOSFET, that's why PENH. Then space W is equal to 13, L is equal to 3. What is this? This is a width and length. Width is
BENH, you say?
P MOSFET, P type and N type. PENH means it is a P MOSFET, P type.
Okay, sir.
It is a command. Why it is PENH? Why it is not only P? It is just a command. That's right. W is equal to 13 micrometer. L is equal to 3 micrometer. Today's lab will be fixing these two. The purpose of this today's lab will be fixing these two. Only these two. Nothing else. Nothing else we will fix. We'll change these. Okay. We'll change this and we will see the what is that? What should I say? The performance, right? We will change this and see the performance. and we will try to find the optimum settings. Settings means W and L. We will try to find the optimum settings for our transistor, okay, for these material, okay, because we are actually using some materials here, right? We are going to see what will be the performance for this material and for this setting. After that, we will change these and we will try to find the exact, no, not exact. We will try to find the best setting possible for this material. Okay, that means when you, okay, let me give you one real life scenario. When you buy some new food for making pizza or for making burger for your shop. Let's say you have a shop, right? Let's say you have a food shop. You buy some different material from the different market, right?
Yes.
You do not know how these will test after making it. So what do you do? What do? You go to the shop and you make a sample copy, right? You make a sample pizza, you make a sample burger, right? And test it, how it is testing, right?
Yeah.
Then you adjust, okay, this chili, I do not know how hot it is. Let's make a burger and see how hot it is. Okay, when you make a burger, when you see the chili is so hot, so what you do? Next time you will give less chili, right? Understood my point?
Yes, sir.
Almost, sir. Please.
Almost. Okay, when you see your burger is less spicy, what you do next?
Less spicy.
You will add more spice next time, right?
Yeah.
So this is the testing. This is the testing. So here we actually are doing the testing. So what you do? We are actually taking the simple possible. This is the simplest possible circuit. The NOT gate is the simplest possible circuit. We are actually testing our element, our material, for the simplest possible circuit and trying to find the best setting. How much chili I have to give, how much width I have to give, how much length I have to give. Understand?
Yes, sir. Yes.
Okay, that is the thing. That is the thing we are trying to do here. Okay. Do not need W and L. W and L we will find later. Just hang on there. W is equal to 13, L is equal to 3, W is equal to 4, L is equal to 3 for NMOS. Now come to the NMOS. Here, this is the MPD. I have written MPD. What is the drain? Blue color, right?
Blue color, number 3.
What is the drain? What is the gate?
This is number 1.
1. What is the source?
Number 0.
0. What is the body?
Also 0.
Also 0. It is N type. That's why it is NENH. W is equal to 4. Why the before one was 13? Why the later one is 4? Because PMOS width always bigger. NMOS width is always smaller. Why? We will explain later when we do the theory. Okay?
Okay, sure.
When you do the theory, we will explain later. Remember this, PMOS width is, maybe in the next class we will need this. PMOS width is 13 and NMOS width is 4. That is not the important thing. The important thing is, remember, NMOS width is always smaller and smaller, let's say small. And PMOS width is always what? Big, okay?
Bigger.
And the length are always almost same. Length are kept same. Length are kept always same. Understood?
Yes.
Okay. Next what? Next VDD. Why are the VDD is connected?
Number 4.
Number?
2 source.
Number 2, right?
Yes.
Where is the other pin?
Other pins.
Other pin of VDD?
Yeah, 0, 0,
0,
0.
0. That's why 2, 0.
Not mentioned,
2
yeah.
and 0. And what is the value? What is the value of the battery? Let's say 5 volt.
5.
Let's say 5 volt. That's why 5. Since it is DC, you do not have to write anything. You can just write only 5. 5 means DC. Or you can write DC, 5 DC.
Okay.
Whatever, doesn't matter. Only 5 is fine. because DC do not have any properties, only the value, right? Okay.
Yes.
Next one is V in, input. So the name of the input is V in. I have written V in. Where it is connected?
Number 1
1. Where is the other pin?
is a 0.
0.
Yeah.
What is the type of the input?
Pulse.
Pulse. It is pulse, not DC. Why not DC? Because if you give DC, either you have to give 5 or you have to give 0, right?
Yeah.
If you give 5, it is 1. So you will get 0 output. If you give 0, you will get 5 output, right? High output. You cannot see any transition from 0 to 1 or 1 to 0. You cannot see rise time, fall time. You cannot see the delay. Can you see the delay? Propagation delay? You cannot see the delay. How much time it is taking for delay? You cannot see it. That's why you will be giving a pulse.
Pulse. Yeah.
Okay. So we'll write pulse. What is the, okay, now come to the, okay, I'm going to give a whiteboard. What is a pulse actually? Okay. Now here, for pulse, at no, not this color. For pulse, at first you will give a delay, right? Delay time. Then the pulse will go up, because the no pulse in the world will directly go up, because there must be some rise time or fall time. Either it is in nanosecond or picosecond or microsecond, doesn't matter. It must have some rise time and fall time, right? Obviously. Then it will remain on for few seconds or few time. Then it will fall down. This is the fall time. Then it will remain off. This is the off time, right? Then it will start again. Understand? Got my point?
Yes, sir.
Okay. Now here, let's use the blue color. This part is called delay time, TD. Okay? TD.
Yeah.
Okay. This part is called what? Rise time, right? So TR. This time is called on time, or I can write on, or you can call pre-or no, with. You can call pulse width, right?
Pulse width.
Pulse width or T on, whatever you say. This time is called what?
Delay time.
Fall time, right? Right? Okay. The total time, that means from here up to here, this is called what? Period. Remember the period?
Yeah.
The
The
period.
period.
The total time, that means the period. Total or period. So how many parameter do you have? Delay time, rise time, on time, that means pulse width, fall time, and total time, that means period, right? This is the parameter you have. And one more thing you have, that is, what is the lowest voltage? What is the highest voltage, right?
Yeah, 0 to 5.
0 to 5. You can write 0 to 2, 0 to 3, 0 to 4, whatever your system is. Whatever your system is. Okay? So this is the thing we are going to write. Delay time, rise time, fall time, and on time, that means the period, no, not period, with, and the total time, that means the period. Okay, my dear? Okay, we're going to share this screen. Okay, now, here we're going to write pulse. 0. The 0 means the lowest voltage. 5 means the highest voltage. 0.3 is the delay time. 0.3 nanosecond is the rise time. 0.3 nanosecond is the fall time. 20 nanosecond, that is the on time, that means the pulse width. And the 40 nanosecond, that is the what?
Period time.
That is the period time, total time. Understood?
Yes.
This is the parameter how you will give the input parameter. Okay, how you will write the input parameter. This is the way. Now, one more thing we missed here. What is that? One more thing. The capacitor, right? The capacitor is the output device. That's why we are not writing it here. we are writing the capacitor where? At the output point, where we have our output, where we will write our capacitor and the output terminal. Okay. So CL is the capacitor, the load capacitor. Is in between where? Is in between 3 and 0, right?
Yeah.
So 3, 0. What is the value of the capacitor? Here there is a mistake. Here it is 50 picofarad. We have written 50 femtofarad. Doesn't matter.
Yes.
PF, P, 50P. We have written 50F, femtofarad. You can write 50P. Oh, by the way, if you write only 50, this is farad. If you write M, small m, this is millifarad. If you write U, it is what? Microfarad. If you write N, only N, nothing else. No farad required, no F required. No capital F required, no, not required. Okay? If you just write N, it is nanofarad. If you write P, it is picofarad. F, femtofarad, right?
Yes.
For ohm, for resistor, if you write only 50, it is 50 ohm. If you write K, kilo ohm, M for mega ohm, then G for giga ohm, something like that. Understand?
Yes, sir.
Okay. Now, this too is very important. Dot tran, dot DC. What is dot tran and dot DC? Let's see the whiteboard. Now, what do you understand by output? What you expect from this circuit to perform? What will be the output of this circuit? Anyone?
Not gate.
Not gate, yes, not gate. If you give a pulse, what will be the output?
The inverse.
Reverse, right? Obviously a pulse, but a reverse. That means
Yeah.
if your input is this, your output will be like this, right? It is 0, 1,
Yes, sir.
right?
Yes, sir.
So this is your V in, we can call it. What you have here in this side, 0 volt and 5 volt, right?
Yes.
That means you have voltage here. And what you have in this axis? In this axis, you have voltage, right? Y-axis. What you have in your x-axis? X-axis. This output graph, input or output graph, right? In y-axis, you have volt. What you have in your x-axis?
T.
T, mean time, right?
Yes.
T, that means time, right? Obviously.
Yes, sir.
So for output is actually the same. Here you have V, also obviously output. In here you have T, right?
Yes.
Based on time, that means according to time. So these sort of graphs are called transient graph. What graph? Transient.
Graph.
That means the graph that is drawn with respect to time, those graphs are called transient graph. So we want to see these, obviously we want to see these. But before that, let's see how many cycles we want to see. This is our high, this is low, right? This is 20 nanosecond, the total is 40 nanosecond, right? We want to see 2 cycles. Understood? We want to see 2 cycles. So here you have 40, here you have 40. 2 cycle means 80 nanosecond. We want to see 80 nanosecond. If you want to see more, you can write more, no problem. So this is the transient analysis. So let's go back. Here you can see dot trend 1 nanosecond, 80 nanosecond. Understood why the 80 nanosecond is given? Understood everyone?
The total.
We want to see 2 cycle
Mm.
as our output. 1 cycle is how much?
40.
40.
40.
How do I know that?
40
Because our
nanosecond.
input is 40. 1 cycle is 40. We want to see 2 cycles, that's why 80.
Yes, sir.
What about 1 nanosecond? 1 nanosecond is the sampling rate, sampling. That means after how many time it will take data and plot the graph.
Yeah. Sample.
Sample, understood? This is
Yes.
a sample rate. So nothing important. But the important thing is the DC analysis. What is DC analysis? This is an analysis we will be doing only for this lab only. For later labs, we do not need it. That means this is the testing part. This is the chili testing part. The chili we are testing, right? This is the chili testing part. Here we will define how much width and how much length we have to give. So let's show you in the whiteboard. Always remember, but before that, let's give you some hint. This is a NOT gate, right?
Yeah.
Here, let's say here you have V out. Here you have V in. Not with respect to time. This is not with respect to time. This is with respect to DC voltage. That means DC voltage versus DC voltage. DC versus DC. This is V out versus V in. DC versus DC, right? That's why it is called DC analysis. Now here, if you give 0 volt, how much output you will get?
1.
1. 1 means 5 volt, right?
Yeah.
Okay. If you give 5 volt, how much output you will get?
0.
Very, very good. Right? We all know it. Right?
Yes, sir.
Because 0 means actually 0. And we are getting 1. Right?
Yes, sir.
5 means 1. We are getting 0. If you give 0, you are getting 1. If you give 1, you are getting 0. That's it, we know it. But what will happen if I give 1 volt? How much output will you get? How much output will you get?
If you give 1 volt,
Yes.
you will get this 0 maybe.
You do not know. You do not know, right?
0, sir.
Here you will get 0, right?
Ah,
Why? Because you consider 1 as your high, right? You
yeah.
consider 1 as high. That's why you're going to get 0, right?
Yes, sir.
Okay. What about 4? If I give 4 volt, what you will get?
All same.
Also same,
because-
right?
Ah,
That means 4 is also 1. That means high. You are getting 0 volt, right?
yes, sir.
What about 3 volt? Same?
সবাই same, sir.
সবাই same. আচ্ছা, ঠিক আছে, okay. Again, for 2 volt is same, right?
Yes, sir.
So this is a common thing people always think, right? People always think. This is a common thought people always think.
Yeah.
They actually make this mistake. This is a mistake because this is unfair. Unfair. Why unfair? Because the high level is so much, low level is so small. If something happened to 5 volt, let's say if the voltage drops, or let's say if there is a noise, the voltage drops, right? It still can recover a lot of things. But what will happen to 0 if a noise comes and make the 0 1 volt? It is not the fault of system. This is not a fault of system. This is the fault of the noise, right? Then the 0 will suffer, right? This is not the case. This is not the case in real life. In real life, the design is drawn like these. 1 is considered as 0, so you will get 1, that means 5 volt. 2 is considered as 0 as well, so you will get 1, you will get 5. It doesn't make sense, right?
Yeah.
So far you have learned so many things, but according to those things, this doesn't make sense. This should make sense. What is high? High means the highest value, 5 volt. What is low? Low means ground, that means 0, right? So far you have learned this. Nobody told you that what will happen if I give a voltage in between. It depends. It depends on the design. It depends on the design of the gate you are using. Normally, ideally, it should be at the middle. Normally, ideally, it should be at the middle. Okay, let's put this data in the graph. For 0 volt, you are getting 5 volt. Use a red color. For 1 volt here, you are getting 5 volt. For 2 volt here, you are also getting 5 volt. For 3 volt, you are getting 0 volt. For 4 volt, you are getting 0 volt. For 5 volt, you are getting 0 volt. So if you connect them using a line, this is your graph, right? So actually, this is not the graph. This is not the graph. Your graph is this one. Understood? So where the graph is going? The graph is going in between 2.5, right? The graph is going through 2.5, 2.5. That is in between 2 and 3. That means less than 2.5 is your low. More than 2.5 is your high. Hafiz?
Yes.
Convinced? We'll prove it. No problem. We will prove it. But got the idea? Got a different idea?
Yeah, different.
Always different idea. Always remember the system voltage, highest value and the lowest value. That is your two end. That means high and low. At the middle, that is the point where your differentiation will happen. More than that middle point is your high. Less than that middle point is your low. Understood?
Yeah.
So 2 volt is less than 2.5. So that is low. You are going to get 1. That means 5 volt. 3 volt, it is more than 2.5. That means that is high. So we will get low. That means 0 volt, that is 0 output. Understood?
Yeah.
Okay, why I mentioned, okay, this is the best solution because this maximizes the noise margin. Here, what is the noise margin? How much is your noise margin? 2.5 volt in the low side, 2.5 volt in the high side. That means a noise can come and can change up to 2.5 volt. 2.5 volt is the flexibility. That means your system can take a noise that is 2.5 volt big or less than 2.5 volt. That is the flexibility. If you have a graph like this, this is 1 volt, right? This is 2. This is 5. This is 0. If your graph goes like this, right? Like the previous one. For 0, it is 5. For 1, it is 0. 2 is 0. 3 is 0. 4 0. 5 0, right? For the previous one, you said, if the graph goes like that, your noise margin is only 1 volt. Although your noise margin for the high side is 4 volt. But which one we will take? We will take the lowest one. Why? Because that is your weak spot. That is your weak spot. No matter how strong you are in other side, doesn't matter. You have a weak spot. That is your margin. Okay, that is your flexibility. So if a noise comes that is more than 1 volt, you are doomed. You are no longer a good position. You are no longer in a good position. If a noise comes that is more than 1 volt, you are in trouble because your noise margin is 1. So how we can do that? We can actually fix that using our design. Okay, I will explain what do I mean by that. So dot DC will be according to the V in, because x-axis you have V in 0 to 5 volt, because our graph will be from 0 volt to 5 volt, and 0.1 is the step. After how many volt we will take data, how many volt we will take data. Okay, the step. Now after writing this code in the text file, what you have to do? you have to save the file. Okay, first of all, you have to save the file as save as. Save as. Click. I'm going to use desktop, but this time I'm going to write .cir or capital CIR. Doesn't matter, small or capital. CIR means circuit file. And most importantly, change the type from txt to all file. Save it. You see there is a file, right? Different type of file. Can you see that? This one. What it is saying? PSpice circuit file, right? If you double click this, your OrCAD capture will open. PSpice AD Lite Edition. Okay? Because the software we already installed, right? We already installed the software. If you double click, your software will be open. I'm going to make it bigger. View. How to make it bigger? I do not know how to make it bigger. Okay, no problem. Now I'm going to run the simulation. Run. If there is any error, here you will see it. Now I want to see the DC analysis first. DC. Here, nothing is here, right? Because we have to show, or we have to see what we want to see. We have to tell him. So here, can you see trace? Go to trace, add trace. Here you have a lot of things: current, voltage, time, power, a lot of things. We want to see V in and V out. V out means capacitor voltage. CL, V1 CL. Can you see that? Capacitor voltage. I'm going to right click V in. I'm going to click VCL. Click OK. So this is the graph. So the green one is the input. I'm going to make it bigger. How to make it bigger? Right click the graph properties. Make the width, change the width. Right click properties, change the width. This is the graph. So this is the output versus input. Here you have input, here you have output. Can you see the graph is going through the middle? Although perfect middle is this one, 2.5 volt. This is the perfect middle. Here 3 volt and 2 volt. Perfect middle is this one. Okay, so your perfect model, perfect middle will be this one. So your graph is going a bit towards the right side, right?
Yeah.
A bit towards the right side. Okay, we can fix that. How? We can go back and we can change the width. What width? Remember 13 and okay. Let me show you in the magnifying. Can you see the 13 and 3, 4 and 3? So I'm going to change the 13 to 12. Okay? And run the simulation again. Yes, DC. Can you see it is going exactly at the middle?
Yes.
So if I change it again, if I make it, let's say 20, it will go towards the right, a lot right. Right? So noise margin reduces. Here, the margin of the noise, let's say it is 2.8 volt. Here, it is 2.2 volt. Because it increases, it decreases the noise margin. Understood?
Yes, sir.
Okay. Now, if I change this one to, let's say, I'm going to make it 8. You will see it is going towards the left side. Got my point?
Yes, sir.
So as you see, the more chilly, less chilly, more chilly, less chilly, something like that. We are going to adjust. We're going to test. See? So if I make it 4 and 3, 4 and 3, you will see if both of them are same, it is going far, far left. If you change the length, what will happen? Far left, right? Not good enough. If you make it 300, like this, right? Not good. If you make it 2, let's see. Again, not good. If you make it 12, and if you make it 3, that is the best one. Now, if you change the MPD, to 400, going like that. If you make it 300, see, so nothing is good. The optimal position will be 12, 3 and 4, 3, right?
Yes, sir.
The best solution is this one, 12, 3 and the 4, 3. So remember this data. So lab number 1, lab number 2, lab number 3, we will be using this data. What is that? For PMOS, it is 12 and 3. For NMOS, it is
3.
4 and 3. Remember this data for your lab number 1, lab number 2, lab number 3, because we are going to use the same material for rest of the lab. So 12 and 3, 4 and 3. The objective of our lab was to find these. Okay, the best setting. We got the best setting, right?
Okay.
Okay. Now we can see the transient analysis. Transient. Again, nothing is here. Let's go to the trace. We're going to see the input. We're going to see the output. The green one is your input. The red one is your output. Change the properties. Make it bigger. Can you see that?
Yes.
Your input is 1. Your output is 0. Your input is 0. Your output is 1. 1, 0, 0, 1, right?
Yes.
You can see some rise time and fall time in your output. Can you see that?
Yeah.
This is because of your capacitor. This is because of your capacitor. Capacitor needs some time to charge. Capacitor needs some time to discharge. Okay, let's change the value of the capacitor. Let's make it nanofarad. You will see more time is needed. Okay, more time. That's why it is not becoming 0 again. Okay, it needs more time to charge. It needs more time to discharge. That's why it is even bigger than your these 20 nanosecond gap. That's why we cannot use nanosecond. Let's say let's use picofarad. Can you see that? It is discharging. It is slowly discharging. Slowly it is discharging, but not fast enough. It is not fast enough. Okay, so it is not fast enough to go down to 0 and go to the high. Understood, my dear?
Yes, sir.
It is not fast enough. So what I can do, I can reduce the, let's make it 20 femtofarad. This is the reason. That's why our graph, not our circuit was picofarad, but our code is femtofarad, right? This is the reason. Let's make it 20. Now you will see more smooth. Okay, let's make it even smaller. Make it 5. See, the graph is more smooth because capacitor is smaller. It takes less time to charge, less time to discharge, right?
Yes, sir.
Okay, so I believe our lab is done today. So we will learn more. Lab is not completed. Lab is done only, just, but not the knowledge, because I need 2, 3, 4 more class to make you understand the whole thing. It is not possible to make you understand one topic in one class. Not possible. Okay?
Yes.
Because a lot of things are interconnected. A lot of things. So you have to understand what should I say? What is the impact of sizing, the W and L? You have to understand the impact, or you have to understand the CMOS design, how the design works, how to design NAND gate, NOR gate, why there is NOT gate, why that one is NOT gate, why we are calling that as NOT gate, right? You have to understand all of those things. In the next class, inshallah, we will learn the CMOS design first. CMOS design, okay?
Okay, sir. Sure.
Okay, inshallah. Do not miss the next class, because if you miss the next class, a lot of things will be missed.
Okay, sir.
Hafiz, can you do one thing for me?
Yes, sir. Of course.
Can you give me the
All.
no, the roll numbers?
Yeah, ready, sir.
Okay, give me the roll number in the group. Okay.
Okay, sir. Thank you.
Okay, thank you.